One of the foundations in mathematics and really a lot of applied areas of mathematics is the notion of a set. And a set is really just a container for elements that we consider to be related or like. So how we choose to relate elements is very much up to us. And really this set, this structure, is just a collection of these related items, which can be numbers, words, symbols, ordered pairs. There's very few limitations on what a set can have. In fact, there really aren't any. Now, usually we denote a set with a capital letter and say, for example, capital M, let's define this to be the set of all students taking a math class. So maybe there are too many students to name, and so we just describe the set. It's just the set of all students taking a math class. So we don't know all the names of the people in there based upon this. But maybe we have a smaller group of people, and we can call this set N. And when we define a set and we describe the exact elements that are in that set, notice that we use these curly braces. Okay, so we have A equals, and this reads the set of elements, and then in between these curly braces we list the elements. So whatever belongs to set A will get listed in here, and we separate those elements by commas. So this describes the set of 3 names, Bob, Annie, and Callie. Then let's take a look at another set. In this case, R is the set containing the elements 1, 2, 3, 4, 5, 6. Well, when I was thinking up this example, I was thinking of a 6-sided die, and these are simply the outcomes of a 6-sided die. In this set E here, you can see that it's the set of elements 2, 4, 6, 8, comma, dot, dot, dot. Well, with that dot, 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 what we're trying to do is to describe the rest of the elements in that set without having to list them, because A, there could be too many, or B, there could be infinitely many. So you can probably see, based upon the pattern here, is that the next element in the set would be 10, and then 12, and then 14, and 16. So what we're really doing here is describing the positive, even integers. Now, we said that these sets could even contain ordered pairs. For example, the set D contains the elements 1, 1, that's an ordered pair, 1, 1, contains the ordered pair 2, 4. Its third element is the ordered pair 3, 9, and then 4, 16. And really what these are is these are the positive integer pairs for y equals x squared. We can see that really the y component here in this ordered pair is the square of the x component. So 2 squared is 4, 3 squared is 9, 4 squared is 16. So the next element in here would be 5, 25, 6, 36, and so on. Now, even these ordered pairs do not have to contain numbers. Here I've described a set S, and this set contains 4 ordered pairs, 1, 2, 3, 4. And what this actually describes is the possible outcomes of 2 coins tossed. And so we probably are familiar with the idea of heads and tails. So there are 4 possibilities you could get on this. We could think of as coin 1, and we can think about this as the outcome of coin 2, and we pair those together, and we can write, one outcome would be where coin 1 is heads and coin 2 is heads, heads, tails, tails, heads, tails, tails. Now, not always do we describe these with ordered pairs. Sometimes it might even be convenient. There are lots of different ways you could do this. Sometimes for convenience, to avoid all the extra commas and parentheses, we might just list HH, HT, TH, and TT, Although there are some functional problems with listing things out this way instead of listing things out this way. But for all intents and purposes, it will not make a gigantic difference in where we're going with this. Now, depending upon our context, we usually have some sort of universal set. So let's define U to be the universal set, and that letter is going to be reserved for the universal set. So by universal set we mean basically all possibilities of whatever it is that we're describing. So maybe what we're looking at is a die roll, the roll of a die, and we'll say this is a fair six-sided die. Fair meaning that it's going to land on one of the six sides with equal likelihood. And so if we were to describe the universe, the set of all possibilities for this particular experiment, we might say, well, U is the set of all possible outcomes, which we know are 1, 2, 3, 4, 5, or 6. Now, we can use a box to kind of serve as the container. So every possible outcome is going to live inside of here. But the reason we do this is because a lot of times maybe we're interested in a particular subset of the universe. So maybe what I want is to look only at the situations where I get an even number. So I'm going to use a circle to denote a set that lives inside of that universe. And that set can at most contain all of the elements of the universe, but since it's enclosed in the universe, it can't have elements outside of 1, 2, 3, 4, 5, 6. So if I want to describe just the even elements that I can get, well, that would be 2, 4, and 6. So within U, I have this set E, and we're not drawing it proportional to size. That's not really important here. There are 3 elements here. Sure, there are only 3 other elements, but usually we just use this as sort of a visualization technique. So 2, 4, and 6. Now we can also describe the size of these sets. We can say the size of U, and there are many different ways to write this, but one way to write that is to say like absolute value, because the absolute value is really kind of describing a size. When you think about numbers like -5, well, how big is -5 relative to 0? Well, it's 5 units away. So the size of U, the length of U is 6 units long. It has 6 elements. 1, 2, 3, 4, 5, 6. Those are the 6 elements. And then the size of E, is 3. Again, there are many different ways to write this. We're going to stick with this convention, but keep in mind that if you look at different resources, they may use different notations, but a size is the number of elements that live inside of that set. Okay, well, at this point, I may also observe the elements that are not inside of E. Okay, so this is going to be an important concept. When you take E and you put a bar over it like that, or I'll put in parentheses, sometimes people will write it with a prime, like E prime. I don't prefer that notation. I prefer the bar over the top, only because the prime we can either forget or confuse it as another symbol. This set, this stands for kind of like not E, all the elements that are not inside of E. Well, if you consider the fact that this is going to be all elements not in E, but still in the universe, well, what are the elements that are not in E, but are still part of that universe? Well, there are 3 other elements in here. There's, we'll just put a 1 over here, and maybe the 3, and maybe the 5 like that. So the elements in E complement, or not E, this is going to consist of the elements 1, 3, and 5. So this is sometimes read as E complement. And earlier I mentioned that sometimes you'll see or hear people say not E. The element's not an E. We also have a notation for membership. How do you assess membership? So think about a set as perhaps like a club or an organization. And if I went back up here and said, define the universe as before, it's the outcomes 1, 2, 3, 4, 5, 6. And I ask, is this a true statement? Is 1 inside of you? This means a member of. Does it belong to? Is it inside of that set? Well, is 1 a member of you? And that's really a question. And the answer is yes, it is. Is 2 an element of you? And that is, the answer to that is yes. What about 7? Is 7 in you? Well, 7 is not in you, right? There's no element called 7 inside of this set. So sometimes we'll put a strike through to indicate that 7 is not an element of you. Now I'm going to remove this because these are now true statements. 1 is an element or a member of you. 2 is a member of you. 7 is not a member of you. That's just a notation that we use to really concisely describe membership. And what that allows me to do, as well as back up here, I could say from before, E, that's the set of all elements, equals the set of all elements X, where X is not a member of E, but X is a member of the universe. Okay, let's unpack that real quick here. We're saying that E complement is the set of all elements X. X is just the name, just describing all the general elements in the set. The set of all elements X, where X is not inside of E, is not a member of E, but X is still within the universe. So what we meant by that is the set of E complement contains 1, 3, 5. Well, those are elements that are not inside of E, that are outside of E, but that are still housed within this outside box. So they're not inside the circle, but they're still inside the box. Okay, we'll go ahead and stop there. This just gives a real brief overview of sets. And in our next video, we'll talk about taking sets and operating on sets in ways in which we could combine them. Maybe we want to take 2 sets and we want to draw a comparison. For example, what elements are in both sets. So if you're talking about students, we might have 2 classes, and we might say, well, I have the name of all students in this class and the name of all students in this class, and I want to find the students that are attending both of those classes. We'll do that in the next video.